And we're live. Hey, Thomas.
Hey, Luca. Awesome.
That's a
So we're
spe-
early today, Friday
it's early
again.
for us. Yeah, because we're in this weird moment of the year where, a part of the world goes to daylight saving time and the other part of the world does that 1 week later. And it's really weird and it throws everything off. So right now we have 5 hours apart from Eastern time, which is why it's 4 p.m. for us. And yeah, it's earlier than usual. Which is
Yeah,
great. But as we prepare for these episodes, that gives us one 1 hour less in the preparation. Um,
yeah,
and also, yeah, but we're baking an episode that is a bit different from the last few ones. Also because I'll be driving the screen this time, so prepare for the worst. And yeah, we'll go into it.
yeah. And
All right.
obviously,
So
it's a holiday today for Italians and for me too, All
yep,
Saints. So it's a
exactly.
very special episode today, not just
Yes.
because you're going to do the programming.
Yeah, I hope the old saints help me out here. Awesome. It's all of them, so it should be pretty. I should be well positioned. Great. So what we would do the last few episodes, we went through examples of how you can take a library of optimizations, optimize kernels, and then use them with a mod like uh, LibGPT. So we took Liger kernels, use them in LibGPT. We published the notebook. The notebook is in the repo, and there's also a Lightning Studio that goes with it. Now the point is, um, it's a lot of work. It's a lot of moving parts, right? And so for a user that comes in and has to use Thunder with Liger, with LibGPT, they basically have to go in and basically reproduce all the code from that notebook to be able to register all the operators and the executors and run things in a certain way. So it's kind of a lot to ask, which is, you can package it up, of course, in your code base and make a function or a class that does a thing. But we thought it would be good over time, not just for Liger, but in general, to have a way where Thomas can write its own Liger adaptation to LibGPT through Thunder and send it to me. And me, as a naive user, I just take whatever he sends me and run it. And I shouldn't have to worry about how Thunder works under the hood. I should just do the thing and say, thank you, Thomas. Now this is like
Yeah, and
30% faster.
even in terms of recording, we had these, you needed to remember like add the executor and the other executor that you needed for technical reasons. And then you had the transforms and you needed to remember to like not pass transform classes, but transform instances and all these
Yep,
things. And so it is neat if you don't have to remember that. I mean, I
exactly. Yeah.
needed
And
to 2 or 3 runs for every step of these, and so anyone else would too.
exactly. So let's take a small picture of what we're talking about here, and then we'll go into the code. One sec. I minimize the screen here, but now I don't see the buttons anymore. All right.
Yeah.
Do you see my screen? Yes, great.
Yes.
Okay, the formatting of this tool is getting all wonky. So I want to be able to see your face, Thomas. That's my
Yeah.
thing right now. Yep.
It's
Okay, great. I need to buy a second monitor. I usually have
yeah.
just
I
one
have
monitor.
been I have been looking at the very wide monitors, and I couldn't
Yeah,
get myself to get one of these. But then,
yeah,
amazingly, like large monitors have not grown disproportionately more expensive since when I
yeah.
was
True.
university
Yeah, my
student.
only problem with the second monitor, it's a stupid problem to have, is that I don't want to become dependent on it. I'm so happy working 2 hours here, 2 hours there, 2 hours there on my laptop. The moment I get used to having a very wide monitor, I won't be able to be happy working 2 hours here, 2 hours here on my laptop. That's
Yeah,
my only work.
I only use the screen for the external monitor for the podcast.
Yeah, that
I
makes sense then. Yeah,
Usually there's
yeah.
so much on the small screen of the laptop that I don't understand. I don't need a larger monitor. So
Exactly.
more confusing stuff.
Yeah, that's my problem too. And which leads me back to this, there's a lot of things going on in Thunder, which is great. So we have, our ThunderJIT call that takes our model, and then it asks for transforms. And here we have a list of them, right? And the order of the transforms is also important because you need to know that the order in which you specify them will dictate how they compose together. Maybe in the future we'll have a way to say, okay, this transform has a certain trait, and so it needs to come after transforms of another trait. It's a lot to think about. Like, I don't want to go in there until we're very mature, right?
I mean, it is tricky for the transforms we had, like in the last few weeks, it wouldn't have mattered because they basically changed separate regions of the traces. But if you have something like quantization and materialization from meta device to the proper device, this will be very crucial because if you materialize first and then quantize, you might run out of memory while the other thing works, right? And so,
exactly. And then we have executors, right? So, whoops.
Yeah.
Where is my pen? Okay, great. So we have executors, and here again we have a list of executors, and the order matters too because the earlier executors will be the ones saying, "Hey, I want that op," and so the claiming process goes in order from left to right in the list of executors, more or less.
Yeah, there are nuances to that, in particular with the fusion executors, right? And I remember when we released the first version of Thunder, that was really tricky because it was hard to override something that a fusion executor would be interested in, and now you can do that, of course.
Yep. And okay. This is the thing. Plus, we have another thing right here, but potentially, which we may have a look into, which is called leukocytes. And the leukocytes are things that you register on the JIT to tell it, hey, I'm seeing a few things in the bytecode, or something that happens in a function being called in the code, and I don't want to make it behave as usual. I want to find a different way to have it execute by the JIT. So I want to intercept something happening in the interpreter, and I want to direct it to a path that is not the usual one. And this is very important in some cases because some models have some quirks that you need to fix. And we'll see an example today with Hugging Face Bird.
We have this.
Go ahead.
We have this all the time when we define the entire mechanism to go from Torch to Thunder. That uses leukocytes extensively. Also, if you register an operator, you could always say replaces this and this. That will also be defining a leukocyte implicitly. But sometimes there are other reasons than operators to have those leukocytes, and so it's good if you can divert any code, because one of the things is that in the end we don't want to. We could special case and edit the model, but it's more neat if we don't have to, in particular if you have like various implementations. And at the same time, it's something where we don't want to like only be able to have Thunder go through parts, but we want the entire thing in one package, right?
Exactly.
The entire model.
So yeah, okay, yeah, exactly. So just to go back to what you were saying a minute ago, the interpreter, we said often, it's a Python interpreter written in Python. So it interprets bytecode and executes the code through Python itself. So it doesn't lower to CPython, doesn't go through CPython. But the reason we built it is to have leukocytes, is to kind of say, okay, when you encounter this situation, then instead of going and just execute like Python, don't do that. And so if you look into gitext.py in Thunder Core, that you will see a lot of leukocytes there, which are the ones that are like taking the execution of an operator, and they're instead saying, oh, just register yourself in this trace and do this and that and track your metadata and so on. So this is the way we enable the whole capturing thing to happen.
And you can do quite nifty things. Like we have one lookacyde for function torch autograph function dot apply. And this means that if you use apply on an autograph function, Thunder will understand that it needs to trace through the forward, insert the forward, and also acquire the backward function in order to be able to compute the derivative. And so you basically have arbitrary control over what happens when you have these lookacydes.
Exactly. And it's an integral part of the magic. Anyway, just as Thomas was saying, when you have executors with special operators registered on them, they end up being leukocyte, but sometimes you need to express leukocytes, and we'll see an example with Hugging This Bird, because for example, there might be some data-dependent path that is not really a data-dependent path, and so, but it kind of breaks, and it would generate probably a graph break or need a special case and other types of compilers. In our world, we can fix that by providing a special leukocyte. But that special leukocyte will only be valid for that particular model in that particular, or model family in that implementation. So as a user, you need to register the leukocytes, remember the transforms, remember the executors. And so as we were saying, this is kind of, a lot to ask. So you may be a scientist that, it's a crazy, crazy scientist that knows how to do this, but then there's the normal guy like me that would like to do something and it's waiting on the scientist to provide it. And so
but you
what
need
is the
red
package?
Glasses, right?
Yeah, red glasses here, and how do we package up all this information and give it to the person, and so that they can run it? And so we came up with a concept, and it's a very simple concept. We're making it log, but actually, because I think it's it will be the final, the way Thunder works for kind of 80% of the people that don't want to look into it too much, but then it will be the way we deliver all these optimizations, just like the lighter ones. We introduced the concept of recipe. So a recipe is a collection of leukocytes, transforms, and executors in a class that will be called in the right order. And so it's where you can put all your knowledge there. Why this is important? And I think it summarizes the why Thunder as well. So I will spend another minute on this part. The world right now is a world where you have models and you have compilers. Well, models like the source of the models, the source code for the models, and you have the compiler, and then you try to say, okay, I'll pass the model on the compiler. I will set a few flags, hopefully, that I know to make it work, or maybe it will just work magically. And then I will have my speed improvements, and I will have something that I can run, right? So if you want to tweak this and to make it work in a certain direction, because then the whole thing will be run on some hardware, right? And the way you run it, the size of the data that you're running will have a strong impact on what trade-offs you want to make when you run this model through the compiler. Are you running distributed? Are you running on a certain device that has a low memory bandwidth and so on? So all these things have very explicit effects on the trade-offs. And so the compiler should know as much as possible what you're trying to do in order to deliver the right optimization. And so one way of tweaking this thing is here, like you tweak flags, you have a number of them, and you say, okay, do fuse as much as possible, or consume as little memory as possible, or and so on. Or in the case of the source code, maybe you can put annotations like with some context. And so you start like indenting your code in a context manager, or you start inputting other types of annotation throughout your model so that the compiler will understand what you're trying to achieve.
And for this, for example, there's autocasting, which can be done with these context managers, or activation checkpointing, where you like recompute some of the things for the backward, or offloading, where you say, don't keep these on the GPU, just store them to the CPU memory, which sometimes is more plenty, and for some of the very nifty hardware is very fast too, and then you get it back when it comes to it, right?
Exactly. And so all these hints are hints that the compiler will then take, or even quantization right now, right? So with Torch.io, great stuff there. Tensor subclasses are one way PyTorch is resolving some of these problems. And so like there are these two actors. With Thunder, we are introducing a third actor here, right? Which is with Thunder, you would imagine, oh, it's in the compiler. In my mental picture, is more like you have a model source code. Today, my handwriting is particularly terrible. You have the compiler, where the compiler is the thing that will fuse kernels or produce the kernels that are going to be ran, right? But then you have another thing here, which can be, where Thunder lives primarily, that interprets your source code, produces code that is amenable for transformations. And here is where you specify all the trade-offs, and you try to make also annotations not really needed, or maybe they're still needed on the source code. If they're there, you understand them. But the point is like the expression of how you adapt your code or your computation, the description of your computation, so that this thing will not have a hard time understanding what you're trying to do. That's where we're spending all the time in. And that's basically where the recipe acts ultimately, right? Because the recipe will tell, okay, I have recipe A that takes model, X, or plus a family of similar models. Like you can have Hugging Face Bird plus Hugging Face Bird, something else, right? Roberta, or some similar embedding models that are written in a similar way, so they have similar characteristics when it comes to program transformation. But it will be different from some other implementation of BERT, because that's quite specific of the way the model was implemented, or maybe it's not at all. Maybe the recipe only deals with optimizing the softmax, the cross entropy, right? or whatever. So the family is really important because some things will apply to a certain types of models. So the recipe will be particularly applied to, or it will be a more general recipe. And then it will produce some sort of optimizations that are better for a certain environment. Like, for example, you could have Hugging Face BERT on distributed plus quantization. And that all these things will be many transformations, many executors packaged up. And so that as a user, as this kind of user, this guy here has a very nice experience just applying that. Then the next step on this, I think, in the experience before you become a full scientist is, how do I take recipe A and recipe B and put them together in a third recipe? So we're not trying to do recipe composition in a fancy way. You just produce a new recipe that takes some of the executors, some of the transforms, and breeds them together to produce another recipe, all the way to creating new ones.
And that's the crucial thing here, right? We want recipes to be really simple in order to make it very light to create a new one. And it could be as simple as, I don't know, something has a different name for their layers, right? I mean, things happen. And it would be a shame if it would be like you needed to dig into the details too much in order to fix something.
Absolutely. Like that. Yeah. So the mantra is, don't make me think. So this guy has other problems. He doesn't want to think about whatever this is busy with thinking. They need to build something, make things happen. So we don't want to have them spend too much time there. And if you think about it, it's kind of the reason why the whole PyTorch Lightning and Fabric and a lot of other libraries were created, was to shield users from too much complexity and still have a very optimized experience. Anyway, now we can take a look at what recipes are, because we've been talking about them in the abstract. And I can just show you recipes.
Yeah, you built that while I was on vacation, right?
Yeah. Yeah, it's really not a big deal. It's just
I was on vacation. The productivity went up all across the country.
Through the roof.
They could give me more vacation to get stuff done.
Yeah. Vacation is good. I got some vacation vibe from you, and I got inspired. All right. So, what is a recipe? Yes. And again, we talked for kind of 20 minutes about it, and now people will say, "Oh, but this is the recipe." I thought it was something much fancier. So,
so
a recipe here.
In the Thunder code, right?
Yeah. Sorry. Right now, I'm in my studio. I use VS Code usually to do things, and we have Liger kernel. Oh, there's a JAX example. I think it's one of the early things that we did. And then Lightning Thunder, I cloned the repository. If you go to Thunder core, you see a recipe file in here. And the recipe file is basically defining a recipe that has a few hooks that you need to override when you create a new recipe. So let's see what the hooks do. Set up leukocytes, or the whole registration, set up transforms, set up executors, and you get default executors here. Default executors come from the Thunder extend default executors, which is the default executors we do. So if you use a recipe directly, you will have kind of the best generic combination of executors out there. And then they have, this is not something you should override, it's just an apply method. And what it does is just call all the various setup methods, register all the various leukocytes directly, and then get the executors, get the transform, and then call JIT with the combinations. That's it.
Yeah.
And the config is a special dictionary there. Here you have another thing that we never talked about, and it's kind of something experimental that we're doing. It amounts to using Dynamo for part of the acquisition. And so like users will be shielded also whether we use Dynamo for part of the acquisition or not. And in this case, we can use Thunder as a Torch compile backend. So it gets, we always talked about Torch compile as our Fusion, one of our Fusion backends, executors. And here you see it at the beginning of the chain, like it will use Dynamo to acquire the thing, and then from the acquired thing, we will go through Thunder JIT again, and then the executors as usual. It's basically something that may help if JIT is not yet ready to acquire certain things. It has the drawback that sometimes Dynamo likes to break the graph, and we always try not to do that. So there's some tension there, but it's okay. You don't need to worry about that because the recipe, whoever creates the recipe will specify, is the compiler ThunderJIT or Torch compile? Maybe compiler is not a good name. We are aliasing the name compiler. So maybe we will call it something else, like I don't know.
Entry point.
Yeah. Comment in the thread, in the comments, please give us a good name for this thing. Thank you very much. Great. And then the validate. Validate is used to say, okay, I created something for Hugging Face Bird. I want to make sure that the recipe validates the fact that the model that was passed in is actually a Hugging Face Bird implementation, because otherwise it will surely break. And so we want to have an opportunity to say, to look at the model before applying the recipe and say, and produce a meaningful error message for users. Instead of stuck trace like that, say, oh, maybe, you shouldn't do that.
Yeah. I mean, for example, when you have something that quantizes and you feed in a model that has been like materialized on the device, there's something that will now work very well. And so you might as well get an error message.
Exactly.
And that's one of the things, obviously, when you're building compilers. I mean, getting this compiler to do the right thing when everything's okay is like much of the focus, but the real art is giving good error messages. And obviously, there's lots of bits in Thunder where we'd like to improve that too. And so here's one thing where we think it's a good opportunity.
Yeah, absolutely. Yeah, it actually will be the focus before we get to a beta version that we release in a few weeks from now. That would be one of the things. And the other thing is provide a list of recipes. So if you go here, we have a recipes directory under Thunder. So Thunder recipes here. And one of them is Hugging Face Bird. So what is needed for Hugging Face Bird is, well, we have a validate thing where we may also extend the support, just not bird for sequence classification. Maybe we will extend it, broaden it a little bit, but this will fail, right? This will raise a value error for model must be this, okay? And then set up leukocytes. We'll set up a special leukocyte, or here in the recipe, we defined a leukocyte class. We may move it from here and make it go into core a bit more. I don't know. But this is the way, yeah, or just make it a dictionary. I mean, the dictionary is not self-explanatory, but yeah, we could make it a dictionary. All right, so you create the leukocyte with the function. That is the function to be replaced. And in this case, if you get into transformers, there was warn if padding and no attention mask. And this introduces something that is I think it's a data dependent.
Yeah, so what it does there is that it checks if you have padding and no attention mask. And so an attention mask, whether you have one or not, is whether there's a tensor or whether there's none for the attention mask. But
Yep.
padding is detected by checking whether there's any padding tokens on there. And that is, of course, data dependent. And at the same time, when you're just wanting to do inference or when you want to do training and you know your training data and your training setup, then it's not like very useful to get the warning there.
Yeah.
And so this is why we eclipse it, because we can't handle it, because it's data dependent control flow, and it's not like something that you would typically want to check at every iteration anyways.
Yeah. Yeah, beautiful. I'm pretty sure that other compilers will special case something like that, right? Because I don't think they want to do into data dependent stuff just for this, right? It's something that you know and you can know.
Yeah, I mean, we see with the next look aside what is the other solution to it. And there you have this is compiling. And so Torch for Dynamo primarily provides something Torch compiler is compiling. And so what the second look aside does here is it returns true if it does. And so there are some places in Hugging Face transformers where they adapt like the model to avoid the data dependent control flow, because no compiler like that, no deep learning compiler, and they avoid the data dependent control flow altogether. And so that is the other option to change the model based on whether you're compiling or not, which is a good thing on one hand because it's very straightforward. On the other hand, it's a bit tricky too, because basically you create a second, well, if it's in Hugging Face, you need like to submit a PR and stuff or keep local changes. And the other thing is that you basically, these things tend to grow. And so once you have this if is compiling, at some point you have like entirely different code flow paths, and that is a bit dangerous too.
Yeah, absolutely.
But
so
here
it's very good consideration, of course. Yeah. So this is easy enough to specify, but of course we cannot ask users to just know all these things or copy paste sections of the code. So this is where you bottle up your setup look sites. We don't have special executors. We will get the default executors, and we don't have transforms. And so here is the basic recipe for Game Face BERT. Let's see where it's actually used. And I think maybe we can go into the tests and sorry.
Test transforms, which you have open.
Is it there? Maybe. I don't remember. Well, let's see.
Or you have
test networks. Yeah, no, it's in test networks. Yeah. And then we have in the test recipes. Okay, great. So of course, there's a test recipe, because I know you were on vacation, but I was diligent and added tests.
There is this thing, like when we discussed how far are we with Thunder, one of the things was, is BERT supported by Thunder? And so I said, well, yeah, it is supported. You just need those two look-asides. And obviously, that's a much worse answer than, yes, it is supported. Here's the recipe.
There is a recipe for it.
Yeah.
Exactly.
So, I mean, it's a nuance when you're really deep into it, but I think it really goes a long way at like having users and walk in their shoes too.
Yeah, absolutely. And so I'm hoping that the recipe, there will be probably we'll keep recipes maybe in a separate repo, maybe in the Thunder repo, or maybe people will keep recipes on their repos. Yeah, would be nice. Okay, so here we load the BERT model. Here in the test, of course, we kind of cut the layers to be one block.
Yeah.
Just to make it shorter for the test, but this is absolutely not useful if you're not running tests. Actually, you should actually use all the layers.
It's for the poor CI, right? I mean, if things take
CI,
1 minute to acquire, that's not a big problem if you do it in production, but it's terrible when you have like 100 tests of them, then you're spending 2 hours on it.
Yeah, absolutely. So this is just for that. And then you import the recipe, and then you call a new function that wasn't there before. It's called Thunder Compile. We had discussions internally. Well, go back a few months, there was a Thunder Compile that had a completely different code path than ThunderJIT has. And then we sunsetted that. And we were going with ThunderJIT, and we are still going with ThunderJIT. JIT is not going anywhere because it's the way you acquire the program, apply the transform, and so on. The lingo is a bit, JAX uses JIT, but what is JIT? It's called just in time, so it's kind of a technical term. And so I think we, like as the user with red glasses on the left before, they would probably, understand compile more. At least it's a verb.
I mean, obviously with recipes, it could be thunder.cook or thunder.bake.
Absolutely.
We couldn't decide between the both, so it's compile.
And then you take it too far, and I think, recipes as far as we go.
If you want to have it really fast, you do thunder.microwave.
Yeah, that would be nice. Yeah. So Thunder compile, and we pass the model, and we pass the recipe, and we're done. And we can just call BERT. Now, Thunderbird here, so past this line, the compilation hasn't happened yet, right? We just created a callable that once called with inputs will actually interpret the model through interpreter.jit and then have lookasides in the GText produce then the trace and so on and so forth. So just, this will be fast, this will be slow, just to clarify expectations here. Yeah. And then we also have a Dynamo recipe here, and we have a basic recipe called Dynamo recipe, which is basically just changing the compiler thing from ThunderJIT to Torch Torch compile, so that you can have the same exact entry point, different recipe. This will be basically the same thing, but it will go through a Dynamo. Dynamo doesn't need the lookasides. Why? Because Hugging Face and kind of Torch compile has been special case to handle each other.
Well, one of the lookasides is this is compiling, which Dynamo in PyTorch directly, so it doesn't need the lookaside. Exactly. The other thing for this check, this warn if padding something, there you will have a graph break, I think, unless they change it. When I first looked, and it had the graph break. But it's at the very beginning, so it's like breaking just this check from the remainder, which is of course good, but has this thing that it kind of makes it runs then code that isn't seen by Thunder, isn't as inspectable.
Yeah. So see what the theme is. Like you either change the code or write the lookaside, right? You either bake it somewhere, either in the compiler or in the originating code or in both, or you have a graph break, or you have a lookaside explicitly. We, in Thunderland, we prefer lookasides explicitly because it tells me exactly how my compiler will treat that thing that is not friendly to deep learning compilers. And I know exactly what I did to it, right? It's not hidden anywhere. And that thing will guarantee that I'm getting the full trace with zero graph break. So this is what we're trying to obtain through this exercise. Yeah. And then you call, and then you start close, and the tests pass, and we're happy with that. Now I will show you some other recipes that we created. I'm working on this one which is the quantized recipe. Yeah, there's a to do here, so it's just work in progress, but it's good. Actually, if you want to join the fun, whoever is reading this is like not complicated in terms of you don't have to get into the guts. So if you followed up until now, probably you understand everything that it goes on in recipes. It's higher level, but there's so much work there to be done, and a lot of creative design work on how to build the recipes that minimally capture what is useful. There will be recipes for quantized, recipes for distributed, recipes for quantized distributed together. It'll be a lot of fun to create the set of recipes that will be useful. So quantized is actually quite interesting because with this first of all, this is to a recipe that we want to apply to
Llama.
Llama LGPT. Sorry, I'm getting old. To LGPT, so we don't need any leukocytes here, or LGPT or whatever doesn't need any leukocyte, right? So so we assume we're running on LGPT here. Whatever model in LGPT, not just one particular model. Let's say every model is supported by LGPT. Here we start seeing something interesting, like we can pass arguments to recipes. So it's not that we need to pass recipes as we did with BERT with zero constructor. We can construct a recipe and also special case it to what I want to do. And in this case, we have a target device. And when you quantize, you have the problem of, sure, you need to transform your computation in such a way that it deals with quantized weights and activations or whatever you need to do there. But then you need to load these weights. And sometimes the weights are already quantized somewhere because you did it before, or you need to quantize them as you load them. And so here is, where the original or quantized state dict are. You need to pass the state dict. We'll see that. Executors, we have the bits and bytes executor for this quantized transform. I think there is a notebook where I took it from. And so you can follow the notebook.
Yeah, the bits and bytes executor is in Thunder proper. But yeah,
but there's a notebook that demonstrates it, I think, somewhere.
Yeah, I think there should be.
Maybe through or dev tutorials.
Yeah,
I don't know, like for example.
Yeah, it used to be a notebook before it got added to Thunder Transforms. Maybe I need to.
Okay.
I need
to.
No
worries.
Make good on the note.
Yeah, I can't remember where I took it from. But
well,
anyway,
we can do it in the recipe notebook.
Yeah, absolutely. Yes. And then you set up the transforms, and the transforms are as usual. You import the transform here, quantization, and then you append the transform, and you do the usual dance. Now, in case of quantization, we also want to materialize. Maybe we want to materialize, maybe we don't want to materialize. But yes, in this case, we do because we support just one recipe per compile invocation. So we're kind of guaranteed that we need to materialize sooner or later. And this happens within the context of the recipe itself. So if you want to add other things, you need to derive from this class and add something else to set up transform or call the parent after, like whatever you want. But you need to come up with a new recipe. This is a bit of a constraint that I think will be very beneficial. It forces people to think things through and not defer the time where an hypothetical user not knowing anything will put things together and it will be a major failure. All right.
Yeah. Don't build a house of cards.
Yeah, absolutely. So we need to be strict on this point. So if you pass the original state dict, you can get an initialization function that will use the original stick dict, otherwise quantized stick dict. And then you pass it to the materialization transform that will take a graph that was based on the meta device, and then bit by bit will move it to CUDA, but in the right numerical precision. And that's it. And then you append to transform, return transform. And I think I have the demonstration somewhere. Yeah, here, quantization. So this is not yet a PR, but it was a good example to demonstrate things. So you have a reference model, and you have the model you want to quantize. It's on the meta device, and then you do stuff with a KV cache. Yeah, let's just drop this.
Yeah, I think you could nowadays. You could have the KV cache on the meta device too.
Exactly. Yeah. This is the first thing I was thinking when I was talking. Yeah. So Thunder compile, then you call it with the recipe, quantize on device, CUDA, original stick dict for the model, or yes. It depends on where you load from, and then you just call it. And so this is the quantization recipe.
Nifty.
Next time, because it's already quite late, but next time we will do what? We will go in and create a Liger, right?
Yeah, Liger recipe. Take
exactly.
1 part lion, 1 part tiger.
Yeah. And what we will do, we already know, right? So we will have all these meta functions, and we will create a new executor, which will return from the setup executor method, register the needed operators on them, and just return the Liger executor. So we would do it if it wasn't too late. And this is the way we will package up all the things that we did in the past 4 episodes, so that everybody can try things out without, being cell order dependent in what they do.
Very good. So
awesome.
Exciting.
Great.
So all new recipes, and actually I'll go and walk over to the kitchen and start cooking soon. So
that's good. Awesome. Okay. Thank you, Thomas.
Yeah, thanks, Luca. And thanks out there. And you have a good weekend.
Yeah, everybody. Yep. Thank you.
See you next Friday. Bye-bye.
See you.